Hello and welcome to this video. In this video we're going to be looking at charging and discharging of capacitors. So we've seen what a capacitor is. It's just an electrical component we can put in a circuit in order to store some charge for a while. And we said that we're going to have to store some energy on this so that we can charge it up and then change what we're going to discharge it across and then discharge it through that. So it acts as almost like a portable battery. So now we need to look at, while it's charging and while it's discharging, what are the changes in things like the current, the potential, the charge that it holds over time? How do these things change? So we first need to set up a simple circuit just to try and show this change. So what we're going to say is, let's start by just having some sort of alternating current supply. So this is just a function generator that will have a sinusoidal supply to it. And we're going to connect this alternating supply to a two-way switch. So we're going to have a point here, a point here, and a point here. And then here we're going to have a capacitor, where a capacitance C. And then in the second loop, we will just have a resistor here. And we'll say this has a resistance R. And then we'll complete the second loop. And this is our circuit. We have one loop where this initially, when it's in this position, let's call this position 1, and we'll call that one position 2. In position 1, we're initially charging the capacitor because we're going to start off with a current that can travel around this loop. Okay, and if it travels around this loop, that means initially the capacitor is charging. So let's actually say, let's move this down a little bit and say when we're charging, okay, initially what happens to the capacitor is capacitor behaves like a short circuit. Okay, so it behaves as if it was just a wire, right? The current flows through it as much as it wants. Which means we'll start off with a maximum. There's no potential across it. We start off with zero potential, and so on. We start off with no charge being held on the plates, which means that when we finally reach the end, once it's fully charged, the capacitor then behaves as an open circuit, because it's now holding, behaves like an open circuit. So the capacitor, when it ends, has stored all of the charge. Therefore, there's no electrons traveling around because they're all stuck on these plates. So if you've then stored all of that charge, it means the charge held is now a maximum, where it initially started as a minimum. The potential across it is now a maximum because we've stored all of the energy there. And the current flowing is now a minimum, because we've actually said that we're starting with it acting as a short circuit so it can flow as much as it wants, but finally when it's an open circuit we say we can't actually have a current flowing. And we can show all of this in graphs, okay, because we know that it's going to be a general increase or decrease or so on, but we need to be able to explain, how does it decrease? Does it decrease like a quadratic? Does it decrease as a reciprocal? What happens? So let's draw our graph. So this is what we see when we take these measurements. Let's draw one graph. So let's label this as the charging graphs, because they will be different to the discharging graphs. And let's say this is how the charge on the plates varies with time. Let's have one here, which is how the potential across the plates varies with time. And then let's have a final one here, which is how the current on the plates varies with time. So first, let's look at how the charge varies with time. Well, like we've said, initially when we first start the current flowing, it behaves as a short circuit, which means that we haven't stored any charge on the capacitor to begin with, right? So at time t equals 0, when we're charging, we start with no charge being stored on the capacitor. We obviously can't go up to a point where we have an exponential increase, because that would require us to have infinite amount of electrons, right? So that means that we have to have some sort of increase that brings us to a maximum, where the maximum is going to be the maximum number of electrons. And the way this happens is we can expect that to begin with, we're going to start storing up the electrons much quicker than we will during the end parts, because if you were to just open the floodgates of electrons, you could grab loads of those as soon as possible, whereas if there's only a few electrons flying out, you then have to work harder to actually maintain those. So it means that we're going to have quite a high gradient to begin with, and it's going to flatten off and become constant like this. And we're going to say this constant here is Q0, where Q0 is just the maximum amount of charge that we can hold on these plates. Now potential is going to follow the same trend, because as soon as we start it, it behaves as a short circuit, which means no energy is lost as we're going across it. There's no energy transfer, so we start at time t equals 0 with no potential across the capacitor. But as it starts to charge up, we start to see that we have to actually do work to maintain those charges there. We're storing that energy, which means we're going to initially start by seeing quite a large increase in the potential, and again it's going to level off to be a maximum, which we're going to call V0, where V0 is the maximum potential that could be across it, and V0 is usually going to be the same as whatever the voltage source is to begin with. Current follows a slightly different trend. If initially we behave as a short circuit, it means that to begin with, the current is actually at maximum. So the current is going to be opposite to the charge, because we're saying if we are storing more charge, it means that our current is decreasing. So we actually start with a maximum current, and it will gradually end up being a minimum. Okay? And this maximum current we can call I0. Now these three graphs perfectly explain how these things can charge. Then we have to look at what happens if we then flip the switch and we look at the discharging graphs. So if we were to then say, I'm going to move this switch here to the discharging, this means that this capacitor is now the source of the EMF, right? Because it holds all the energy, and as soon as we flip that switch, then the energy is going to flood out of it and then start going across this resistance. So if I then move down, I can say that for the discharging graphs, I can have similar graphs where I'm going to investigate how the charge varies with time, how the potential varies with time, and finally how the current varies with time. Okay, now as we're discharging, we know that we have to start off with this capacitor being fully charged. It has to currently hold all of the electrons on the surface of these plates, which means we start out as a maximum, and then when we allow the current to flow, the electrons are then going to leave the capacitor, and then your capacitance is, or the charge that you've stored, is gradually going to decrease. So we're going to see a graph that starts off as a maximum and then gradually falls to a minimum, and this maximum is Q0. Okay. The potential is also going to follow a similar trend. We're starting with a fully charged capacitor, meaning that we have a maximum amount of energy stored there. As soon as we flip that switch and it allows to discharge, all of that energy floods out. The potential across it is going to decrease, which means that we end up with the same style graph, okay, where it's going to end up at a minimum. The current, once again, is going to follow the same thing it did when it was charging, because as soon as we flip that switch, the current is going to fly out, the charges are going to start flowing around. You start off with a maximum, and as soon as all of that energy has been transferred out of that resistor, we then end up with a minimum. So we start off with a maximum, we end up with a minimum, and all of these graphs follow the same trend, where they start at a maximum and they end up with a minimum. However, there is an anomaly with current. The charge and the potential follow the same trends in both cases, whereas the current only ever decays. Okay, there's only ever a decay of current. Now, from these graphs, we have to be able to put a function to them. We have to be able to specify what actually can we do to calculate the charge at every single time along this graph. And to do that, we need to look at the formula sheet. So the derivation of these equations is a little bit more complicated, but we can explain where the equations come from and why they are the way they are. So for the charging graphs, you will have a equation on your formula sheet that tells you about the charging of a capacitor, and it will tell you that Q, so I'll write it underneath. So this graph represents Q equals Q naught 1 minus e to the minus t over RC. Okay, so I'm going to put this in a box because this is on your formula sheet. Okay, so you don't have to memorize this one. But this basically means that this e to the minus t over RC is an exponential decrease. So if you're doing 1 minus that, you're actually going to end up with beginning at an exponential increase and then leveling off at the maximum Q naught, which is basically saying when t tends off to infinity, this tends off to be basically 0. So you end up with just 1 times Q naught, so you get Q naught. And since this follows the same shape, we can say it follows the same function, but with different variables. Instead of having Q and Q naught, we have V and V naught. Now, I'm not going to put this one in a box because it's not on your formula sheet, but the discharging ones are. So if I manage to scroll up a tiny little bit, the discharging ones actually follow a simpler expression. These are just exponential decays. So we end up with Q is equal to Q naught times e to the minus t over RC. And again, this follows this similar trend, but this one is not on your formula sheet. Okay, and now actually we can see that this decay of charge is, or this decay relationship or behavior is actually the case for both with current. So in both cases for current, we can always write I is I naught e to the minus t over RC. Now the only formulas that are given to you in the formula sheet are the charge, discharging and charging. This is why we go through these graphs so that you can know which ones you can actually apply these to. From this graph, from this video, you should take away the fact that through charging and discharging, charge and voltage will always do the same thing. So you can always separate or substitute V for Q in any of the equations, but current will always decay. You can only ever follow the decay equation for current, and you should be able to use these expressions. Now there's kind of some terms that we haven't really explained in these equations, and that's because I'm going to explain them in a separate video, specifically looking at how we can manipulate these equations and some of the maths behind it. Thank you for watching.